Okay, Newton's first law of motion. When we are talking about Newton's first law, it simply states that if an object is at rest, it will continue to be at rest, and if it is in motion, it will continue in this motion with the same speed and same direction. It means the velocity will not change unless acted by an unbalanced force. Not a balanced one, unbalanced force. The net force should be not equals to zero. So that is the statement. Now, majority of the student have this confusion that the when the forces are balanced, it is only at rest. No, there are two conditions when the forces are balanced. It means net force is zero. What are those two conditions? First is object can be at rest, velocity is zero, acceleration is zero. It will remain at that rest. And object is in motion, velocity is not equals to zero, but acceleration is zero. It means the velocity is not changing. When I say the term velocity, I mean to say both direction as well as magnitude. So it will stay in the motion, same speed and same direction. That is Newton's first law. It is also known as law of inertia. In some of the books, you will also call this as law of inertia. Inertia is nothing but a property of a matter to resist the change of a motion. More the inertia, more an object can resist to change its motion. If it is at rest and it wants to move, more the inertia, it will be difficult for you to make it in motion. Less inertia, it will be easy for you to move. Okay, so inertia is directly related to the mass of an object. More the mass of an object, more is its inertia to change its motion. Okay, so there are few examples. An object at rest, this stone will remain at rest forever if there is no unbalanced force acting. Even though the same force is applied on both the side, it will stay at rest. But if I want to make a move, so I need to apply an unbalanced force. So in this case, only in this direction, the force is acting. As a result, this will be able to move. Similarly, if a football is at rest, it will stay at rest. Now you are applying an unbalanced force. It will continue. Now it will continue to move in the same direction, but we know that the ball is acted by the weight as well as air resistance is acting. As a result, it is changing its motion. So these all are examples of first law. This is only theoretical part. You just have to know about it. Now coming to the Newton's third law. Second law we will discuss after this. Now, Newton's third law, please make a note of this. IB never expect this statement. I have seen many students writing it down. Every action has an equal and opposite reaction. But in IB, that statement is considered as incorrect. So I know it is quite common to know Newton's third law, but how we will write it down? It states that when one body exerts a force on another body, the second body will also exert the same magnitude of force on the first body but in opposite direction. The statement can be written in a different way, but the meaning should be the same. So you can say if object A is applying a force on object B, then object B will also apply a same force but in opposite direction. And that is why I have written a negative sign here. So always remember this is the correct statement for your Newton's third law. Not every action has an equal and opposite reaction. That will be considered as incorrect. Now, these are the 3 points which are very important for us to remember whenever we are dealing with Newton's third law. What are those 3 points? First, always acts on two different objects. We will take some examples. So these two forces are acting on two different objects. A is applying on B and then B is applying on A. So these are two different objects. So action and reaction never acts on the same object. It will always be on two different objects. I know it might be confusing. We will discuss some examples so you will get to know. Nature of forces, that means the type of forces will be the same. So this action and reaction should be the same nature of force. Now, what does that mean? Same nature of force means if the action is a gravitational force, then reaction should also be a gravitational force. If action is a magnetic force, then reaction should also be the magnetic force. So the two forces that you are applying in Newton's third law should be of the same nature and acting on two different objects. And the last is the same magnitude, as we already know in the definition of the law, and opposite direction that we already. So these first 2 points you need to understand what are the pair of forces in Newton's third law. Now let us take this example, and I want you to just have a thought for a while. A book is kept on a desk, okay? A book is at rest and it is kept on a desk. Now, what are the forces of action and reaction according to Newton's third law? What are the two forces acting in this scenario? If you are saying the normal force and the weight are the Newton's third law equal and opposite pair of forces, then you are incorrect. Now that's the reason why I told you it always acts on two different objects and the nature of force will be the same. Now here the normal contact force is a different type of force. This is the weight, this is a gravitational force, and this is a different type of force. And the weight is acting on the earth, so earth will also act of the book is applying a force on the earth, the earth will also apply the same force on the book. That will be considered as the Newton's third law of pairs. So make a note of it here. Please make a the Fn is equals to mg, that is for sure. But these are not the interacting pair of forces as per Newton's third law. Because the force on book by the earth is equals to the force on earth by book. Try to understand this statement. Force on the book by earth is equals to the force on earth by book. So there are two objects. One is the book, one is the earth. So these are equal and opposite. I'm not saying they are not equal and opposite. They are equal and opposite, but they are not the Newton's laws of pair of forces. So the correct answer is the gravitational force, the gravitational force of on book by earth is equals to the gravitational force on earth by book, and that too in negative. So earth is applying a force on the book in this direction. The book is also applying a force on the earth in this direction. Okay. Now look in the second example. A car is moving in this direction and there is a very small bug which is moving in the opposite direction and it hits the windshield of the car. Now they will apply a force on one another. So I'm asking you, will the car will apply more force on the bug or the bug will apply more force on the car? It is the same force, correct. Then why the bug is got more injured and there is nothing on the car? The car has more inertia. So look, the force experienced by the small bug is same as the force experienced by the car due to collision, according to Newton's third law. But due to the car having the more mass, we know the formula is F equals to ma. Now the forces are the same, okay? So the mass of the car, if I want to write down, mass of the car into acceleration of the car is equals to negative of mass of the bug into acceleration of the bug. Now we know that mass of the car is much, 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 much greater than mass of the bug. Therefore, can I say the acceleration of the car will be very less than the acceleration of the bug due to its huge acceleration?
Yeah.
It is having more speed, and if it is having more speed, then it will get more injured. So that is what it is according to Newton's third law. So I hope Newton's first and the third law is clear. You can have a read from different internet sources about the theory of Newton's third law, you can have Horder publication book, which is another good one to refer so that you can have a read from there. I will upload a link under the content section on website for the Newton's third law. For more detail, you can have a read from there. Okay. Now coming to the most important one, Newton's second law of motion. So everybody knows that the formula for the Newton's second law is F net is equals to mass into acceleration. So you can say when a resultant force acts on a constant mass object, the acceleration of the object is directly proportional to the resultant net force. So acceleration is directly proportional to the resultant net force for a given constant mass object. This is given in your data booklet as well. Always remember this is the net force in Newton. M is mass in kilogram, acceleration in meter per second square. Always remember the mass has to be in kilograms. If it is given in gram, we have to put it in kilograms. So 1 Newton is equals to 1 kilogram times 1 meter per second square. That would be the conversion of Newton into fundamental units that we have already covered in our previous classes. It's a vector quantity. Direction will be the same as that of the acceleration. In whichever the direction the acceleration is there, the same direction will be for the force. I hope you know all these things. This we will discuss in a while in the next part. It is in terms of momentum, we can also define the force. The net force acting on an object is directly proportional to the rate of change of momentum. How fast your momentum is changing, that will be directly proportional to the net force acting on that object. So momentum is denoted by P. Delta stands for change. So delta P is the change in momentum over change in time. Momentum we'll discuss. It is the mass times velocity. So this is final momentum, V is final velocity, U is initial momentum, initial velocity divided by time t. So mass is constant, so I take it out from the factorize and I take it out. So what is left is V minus U over t. And V minus U over t is nothing but acceleration. So that is how we get the formula of F net. So now how we will apply the Newton's second law, that is the idea we need to know. So the net force is always driving force minus resistive force. Now we need to understand what is driving force and what is resistive force. Always be very clear in your mind. Driving force will be the force acting in the direction of motion. So if an object is moving in this direction, whatever the forces are acting in this direction will be my driving force. Similarly, if an object is moving in this direction and there are few forces which are opposing it, that will be considered as resistive force. It can be more than one also. So all the forces acting in the opposite direction of motion will be my resistive force. So in short, I will call F net equals to dF minus Rf. This equation we will apply in the coming part. And F net is nothing but mass into acceleration. So mass into acceleration equals to driving force minus resistive force. Okay, now we will apply the Newton's second law. And on a horizontal plane, a block of mass m1 is placed on a rough surface. The datas are given to you here. It is moving in this direction with an acceleration a. The tension is, the force applied is T, let us say. The T is 8 Newton, m1 is 2 kg. Coefficient of dynamic friction, kinetic friction or dynamic, you can say, or coefficient of static friction, G is 9.8. If it is already moving, then we will use the kinetic friction, or you can check whether it is moving or not as what we have learned in the friction. Here you have to find out the acceleration of the block mass m1. Give it a try. So the first step, as I mentioned in my previous sessions also, always step 1 should be your drawing the free body diagram. So if I draw m1, G is acting downward, normal force is acting upward, the T is the applied force and it's a rough surface. So friction will be applied. So second step is Fn is equals to mg. So m is 2, g is 9.8, that is 19.6 Newton. Step 3, find friction maximum, which is nu as into Fn. So nu as is 0.15, Fn is 19.6. How much you are getting this?
I got this as 2.94.
So friction is 2.94 Newton. Now we see that this friction maximum static is less than the applied force. So I
Yeah.
make a T is greater than F maximum. So I know that now the friction will be nu K into Fn. Even though in when we know already that it is moving, we can neglect this and we can directly calculate nu K is 0.1 into 19.6, which is 1.96 Newton. So this is my friction now. Now, step 5 is making equation for mass, making equation, which equation? F net equation. Now, F net equation is what? F net equation is F net equals to driving force minus resistive force. Now, look at the FBD. This is my driving force. This is my resistive force, and I know both of them, right? So, and F net is I'm making equation for M1, F net equation for M1. So, M1A is equals to T minus friction. M1 is 2A, we need to find out. T is given 8, friction is 1.96. Just solve for 8. 8 minus 1.96 divided by 2, which is 3.02, or I can simply say 3 meter per second square is my answer. Simple. So please check it again what I did. Step 1, please follow the step. If you follow the step, I can guarantee you you can solve every question. Step 1, draw free body diagram. Step 2, find out the normal force. Step 3, if it is already moving, you can neglect this. So you just find out the friction, then make out the equation for all. If there are more than one masses, you have to make F net equation for each masses. So for each mass, you have to see what is the driving force, what is the resistive force. And then just make out the equation, put up the values and calculate. Shall I give you one more question? Try this question. Be quick. Use the same steps that we did in the previous question. The only change is now the force is acting at an angle 50 degree. So draw the free body diagram and follow all the steps. Do it fast. Yeah, so always remember, make sure you draw the free body diagram first. So in this case, it is M1G downward. Now this is acting at an angle. So this component we know now is T cosine 50. Here it will be T sine 50 plus normal, both in the same direction, and then friction, right? So the second step is Fn plus T sine 50 is equals to M1G. So you will find out Fn, which will be mg minus, so 2 into 9.8 minus T is 8 sine 50. So once you calculate this, you will get your normal contact force in this case. So the normal contact force you will get something around 13.4716 Newton. Then we already know it is moving. It is moving. So you can say that the friction will be nu K into Fn. Nu K is 0.1 into 13.4716. You will get 1.34716 Newton. Now, once we have the friction, we have the driving force here is T cos 50. So we will make out equation M1A is equals to T cosine 50 minus friction, which we already know. So acceleration will be T cos 50 is 8 cos 50 minus 1.34716 divided by 2. Once you solve this, you will simply get 1.9 meter per second square. That's it. Is it clear? So these are called connected bodies using a string or a rope or a chain or anything it can be. So here there are three different masses, M1, M2, M3. The masses are given to you. I am applying a force F which is 12 Newton. Calculate the tension in the each string and the acceleration assuming no friction. Okay, assuming no friction. Take G as 9 point. Here G is not required anyway. So assuming no friction. So you have to find out the tension in the each string. These are one string, this is second string. So you can assume any one as, but these are two different strings. So two tensions and the acceleration of this entire system. Give it a try. Okay. So the first part I would start with, let us say for M1. So for M1, I know that F is applied here, and I know that a tension is there because it's a rope, and tension is always away. And let us say this is T1. So what would be the F net equation is M1A is equals to F minus T. Now I know that there's no friction and Mg is equals to Fn, and I don't need to find out Fn because I don't need to have friction here, so no need to draw the vertical forces. Even though if you want to draw, you can draw, but I'm only considering the horizontal forces because I'm making this equation in the horizontal direction. So this is for M1. Similarly, for M2, I know that there are two ropes, so it will have two tensions. Now this rope has a tension T1, it will remain the same. But if I'm taking M2 as my object, the tension will be away from it. So this is T1. Similarly, T2 will be here and this is moving in this direction. So my T1 will be considered as driving force. T2 will be considered as resistive force. It is a little bit dealing here. Just a second. I don't know why it is getting delayed. Anyway. So if I want to make F net equation, it will be M2A that will be equals to uh, T1 minus T2. Similarly for M3, who is moving the M3? This rope, right? Which is tension T2 here. So there is only one force acting T2. So M3 and there is no resistive force. So I will only say M3A is T2. Now as they are connected, they all will have the same acceleration. Now we want to find out acceleration T1 and T2. That is what they are asking. Tension in each string and acceleration. So always remember there are three variables T1, T2 and A. So we need three equations. Equation 1, 2 and 3. So in physics, such type of problems you just have to add because you look, this is negative T1, this is positive T1. This is negative T2, this is positive T2. So if I add all these equation 1, equation 2, equation 3. So if I all add all these three equation, what I will have adding equation 1, 2 and 3, I will have M1A, M2A, M3A equals to F minus T1 plus T1 minus T2 plus T2. So if you look here, minus T1 plus T1 get cancelled out, minus T2 plus T2 get cancelled out. And everything is M1 plus M2 plus M3 times A. A is a common, so I take factorize is equals to F. Now if you look in the question, F is already known, M1, M2, M3 is known. So this is M1 is 3 plus 2 plus 1. 3 plus 2 plus 1 times A is equals to 12. So 6A equals to 12. So A is equals to 2 meter per second square. So once we find out the acceleration, right, now we can easily find out T1 and T2. So you can simply say M3 using equation 3. So M3A is equals to T2 using equation 3. You can see M3A is T2. So we now have A, M3 is how much? 1, right? So A, that simply means 1 into A is 2 is equals to T2. So we got T2 as 2 Newton. That is our one tension, and the another for T1 you can use equation 1, or now we know T2 you can use any equation. So I'm using equation 1, which is M1A equals to F minus T1. M1 is 3, acceleration is 2, F is 12 minus T1. So you can add T1 on both the side, or you can rearrange this equation. So T1 will be 12 minus 6. So T1 is 6 Newton. Simple. So these are my answers. 2 Newton and 6 Newton is my tension T1, T2 in the two strings, and acceleration is 2 meter per second square.